So here we're into inferential statistics. What is inferential statistics, or what are inferential statistics? The term refers to a set of procedures for deciding how closely a relationship we observe in a sample corresponds to the unobserved relationship in the population from which the sample was drawn. And there are a couple of ideas here. In social science, we very rarely have information on an entire population that we want to know about. I'd say every eligible voter in an election, for example. That's unobserved by us. In order to gain some sort of conduit of information about that unobserved population, we draw a sample. And in that sample, we want to make inferences based on that sample about what the population really looks like. So let's talk about populations here. A population may be generically defined as the universe of cases the researcher wants to describe. Every eligible voter, every student enrolled at a certain university, every campaign donation in a recent election, every country of the world, every state. Whatever universe of cases we want to know about and describe, that would be a population. A characteristic of a population, an attribute of a population, such as, for example, and this is an example that is followed through this chapter, such as the mean level of support for the Democratic Party as measured by the by now familiar Democratic feeling thermometer. Characteristics of populations are called parameters, population parameters. Population parameters, by convention, are always symbolized by Greek letters. So, for example, a population mean is symbolized by the Greek letter mu. Although it's not on this slide, a population standard deviation, for example, is symbolized by the Greek letter sigma. Ordinarily, as I previously referred to in the previous slide, ordinarily we can't directly observe population parameters. Now, if we have a census, the defining characteristic of a census is that it is a measurement of every element, every member of a population. But as I've said, it's unusual in political science to be dealing with census information, although it's not unknown, of course. Ordinarily, we're dealing with samples. So let's talk about samples. A sample is a number of cases or observations drawn from a population. Here's another convention. A characteristic of a sample, such as the mean level of support for the Democratic Party, is a sample statistic. So we refer to population characteristics as parameters, and we refer to sample characteristics as statistics. So if we took a sample out of a population and calculated the mean level of support for the Democratic Party on a scale of 0 to 100, we'd be dealing with a sample statistic. Sample statistics are symbolized by regular letters, sometimes with embellishments. A sample mean, for example, is symbolized by X with a bar over the top, called X bar. Sample standard deviations are represented by the ordinary letter S, as opposed to sigma, which is the population parameter. Let's say we have a student polling group, and this group wants to estimate the mean Democratic feeling thermometer rating, mu, in a student population. Let's just say the student population, the total population is like 20,000 students. So the plan, of course, is to take a sample of size n. Notice, this is another thing, notice that sample sizes, strictly speaking, should be represented by lowercase n, and population sizes, strictly speaking, represented by uppercase n, although computer software routinely violates that rule, but here we'll follow it. They plan to take a sample of size n and calculate the mean Democratic feeling thermometer in the sample, X bar in the sample. And though it's not on the slide, in the example that's followed through in the book, they take a random sample, and we'll see why that is, of size 100, and they calculate in their student sample of 100 a mean feeling thermometer rating of 59 on a scale, of course, it runs from 0 to 100. For the students, here's the inferential question, or here's the important question. Let's say they take that sample mean, they get 59, and they don't know what mu is. That's the whole problem of inference. They don't know what the population mean is. The question then becomes, how accurately will X bar, say 59, estimate mu in the population? That's the essential question of inferential statistics. There are three factors that determine how accurately X bar observed in a sample estimates mu, which exists in the unseen population. The first is the sampling procedure used. And as noted, the sampling procedure used must be a random sample or based on random principles. Intuitively, the size of the sample n will determine how accurately X bar is going to estimate mu. This is fairly straightforward, and it's true that the larger the sample you take, the more accurately your sample statistic will reflect the population parameter. Here's a less intuitive one that students sometimes struggle with. The third factor is that determines how closely X bar is going to mirror mu is the amount of variation, or sigma. There's sigma. That represents the population standard deviation, which is the measure of variation in an interval level variable. The amount of variation in the population parameter being estimated. If there's not a whole lot of variation, say, in democratic feeling thermometer ratings in the student population, it's going to be easier to get an accurate estimate of the population mean than if scores or ratings of the Democrats are spread out. Let's talk a little bit about the sampling procedure, and as I guess it's redundant, but I keep talking about randomness. Randomness is it's a beautiful process. We've been here before when we've talked about random measurement error versus systematic measurement error, when we talked about experimental designs as being superior to control comparisons because they use a random allocation or random assignment of subjects. Well, here's the beauty of randomness is here again, and its appeal is identical. In taking a random sample, the researcher ensures that every member of the population has an equal chance of being chosen for the sample. So, hypothetically, let's say the entire student population, capital N there, of 20,000. If you have a population of 20,000, each student in that population has a 1/20,000th of a chance of being chosen for the sample. So there's no selection bias. There aren't some students in the population who are more likely to be chosen for the sample than other students. A random sample eliminates selection bias, which we've talked about before, a source of systematic error. You know, if you take a sample of student population, I don't know, by standing in the student union and interviewing or polling students who walk by, or standing in the library and doing that, or standing at the bus stop, you're going to have selection bias because there are non-random processes that caused some students to be in the student union as opposed to elsewhere, or the library, or the bus stop as opposed to elsewhere. And those non-random processes are going to introduce sampling bias into the sample, or selection bias into the sample. By having a random sample, you don't eliminate error. You introduce random sampling error. But the good news there is we fully understand how to estimate the size of random sampling error. So the bedrock is start with a random sample. And once you've got a random sample, we have a very good understanding in inferential statistics how to estimate how much error is contained, how much random sampling error is contained in a sample. So let's talk about a little bit about this really important concept. Random sampling error is defined as the extent to which a sample statistic, the thing we're looking at, the thing we've measured, the average or the mean level of democratic support, feeling thermometer support in the sample, the extent to which a sample statistic differs by chance from a population parameter. So, population parameter, in this case it will be mu, which we can't see, equals the sample statistic, which we can see, we've calculated it, plus random sampling error, which we can estimate. Now, the random sampling error is not a certain thing. There's uncertainty in it because it is a random process. But we can estimate the bandwidth, the size of that random sampling error, so we can have a pretty good idea, given our sample statistic and the size of that bandwidth, where that population parameter lies. More formally, mu, the unseen population mean, is equal to x bar, the calculated sample mean, which we have, plus random sampling error. So our student pollsters are looking at this, and they know what x bar is. Let's say they've calculated x bar at 59, and all they need to do, although this is an important thing to do, is figure out how much random sampling error is contained in that estimate 59, and then calculate the boundaries, the likely boundaries of the true population mean mu. So now the question becomes, how much random sampling error is contained in a sample statistic? And again, to reiterate, the answer to that question depends on the sample size. We'll look at that. We'll look at that relationship. And again, depends on the amount of variation in the population parameter, sigma. And here is the bedrock foundation formula for inferential statistics. Random sampling error is equal to sigma, that is the amount of variation in the population, divided by the square root of n. So let's dwell on this for a minute. Notice that n, the square root of n, is in the denominator. That means as n goes up, random sampling error declines. The relationship is inverse. So I guess, again, that's not counterintuitive. The bigger the sample, the less random sampling error you're going to have. Notice that sigma, the measure of variation in the population parameter, is in the numerator. So as sigma goes up, as variation increases, random sampling error also increases. So that's the nature of that relationship.